Okay, and for what we have in this last section, we have working with orthogonality. Okay, we have the Gram-Schmidt process. And say we have a given basis, okay, where we have vectors for non-zero subspace W of Rn. And here with the Gram-Schmidt process, okay, we had that V of 1 is equal to X of 1, V of 2 is equal to X of 2 minus the ratio of the dot product of x2 and v1 with respect to the dot product of v1 and itself v1. And as we go to v3, you have a little pattern here. So you have x of 3 minus x of 3 dot v1 over v1 dot v1 times v1 minus x3 dot v2 over v2 dot v2 v2. And you have, just for the algorithm itself, we have in the general case, and we have going from x to v, we have then that each vector v that is formed, this will be part of the orthogonal basis for w. And okay, now we have in this particular case, now for the spans regarding v and x, okay, these will be equal to each other, where we had the subscript to values k to be such that we have 1 is less than or equal to k is less than or equal to p. Now, in the case of taking what we have with the Gram-Schmidt process, it says to use it to produce orthogonal and orthonormal bases. Now, orthonormal, again, you have, if the vectors are not unit vectors, we convert them as such. Now, we have with x, okay, we have 3 by 1 vectors, whereupon we have x1, we have 3, 0, negative 1, x2, we have an 8, 5, negative 6. And with the Gram-Schmidt process, okay, v of 1 and x of 1 are one and the same. Okay, so you have 3, 0, negative 1. And we have for v of 2, again, we have equal to x of 2 minus the ratio of the dot product of x2 and v of 1 all over, again, the dot product of v of 1 times itself times v of 1. Now, concerning the dot products, okay, so you have x of 2 times v of 1, the dot product, so you have taking the transverse of x of 2, so you have 8, 5, negative 6. And again, v of 1 and x of 1, those are the same, where we have 3, 0, negative 1, 8 times 3, 5 times 0, negative 6 times negative 1, add up to 30. And for the dot product of v of 1 and itself, again, you have taken the sum of the squares of 3, 0, and negative 1, where we have to come out to 10. Okay, so what we have plugging in for v of 2, okay, so you have x of 2, 8, 5, negative 6, minus, okay, you have 30 over 10. In this case, this will be minus 3 over what we have for v of 1, which we had at 3, 0, negative 1. So you have 8 minus 3 times 3 is negative 1. 5 minus 3 times 0 still remains at 5. Negative 6 minus 3 times negative 1. You have negative 6 plus 3, which will be at negative 3. So you have your v of 1 at x of 1 with 3, 0, negative 1. And your v of 2 comes out to negative 1, 5, and negative 3. So these two vectors will form the orthogonal basis. And if you were to map together, you have like 3 times negative 1 is negative 3. 0 times 5 is 0. And you have negative 1 times negative 3 is 3. Negative 3 plus 3 is 0. So the dot product of the vectors in the orthogonal basis will be 0. And if you notice, we don't have unit vectors, but if I were to take each one and divide by their respective magnitudes, okay, now we have for the orthonormal basis, okay, so you have each of v of 1 and v of 2 divided by their magnitudes. And for what we have in this particular regard, okay, so you have v of 1 over the magnitude of v of 1, v of 2 over the magnitude of v of 2, and now the magnitude of v of 1, you had the sum of the squares of 3 and negative 1, which would be at 10. That of v of 2, you have to come out to 35. You know, 1 squared, 5 squared, negative 3 squared comes out to 35. And for the orthonormal basis translation, again, we have 3 over the square root of 10, 0, and negative 1 over the square root of 10 for the first. For the second unit vector in the establishment of an orthonormal basis, have negative 1 over the square root of 35, 5 over the square root of 35, and negative 3 over the square root of 35. Now, let's say if we have a trio of vectors in x, where upon we have x1 is equal to negative 1, 0, 1, 3, x2 we have at 0, 4, 1, 0, and x3 we have at negative 2, negative 7, 0, and 0. Now again, we have v of 1 is equal to x1, so we still have negative 1, 0, 1, and 3. Now for v of 2, if I run it, okay, again, through the mill, with the Gram-Schmidt process, the dot product of x of 2 and v of 1 comes out to 1. The dot product of v of 1 and itself comes out to 11. So we have x of 2, 0, 4, 1, 0, minus the ratio, the dot product, so you have minus 1 11th of v of 1, so you have negative 1, 0, 1, and 3. And for the difference, okay, now this will come out to 1 11th, 4, 10 11ths, and negative 3 11ths. And what we can do is that we can get rid of the ratio and rewrite this going from v2 to v2 prime. And we can just multiply the terms or the elements by 11, whereupon we have 1, 44, 10, and negative 3. And working with x of 3. Okay, so we have v of 1 established, and we have v of 2, thus v2 prime set up. Now for v of 3, okay, so we can say that we have x of 3, and again, looking for the dot products in x of 3 and v of 1, and we have x of 3 and v of 2 prime throughout. Now we have concerning the dot product, so that between x of 3 and v of 1, again, you have negative 2 times negative 1 is 2, and we have negative 7 times 0 is negligible. Everything else, 0 times 1, 0 times 3, also negligible. So the first dot product is at 2. And again, we had the dot product between v of 1 and itself again. So that is going to be at 11. Now, in the case of what we have for the interaction between x of 3 and replacing v of 2 in the Gram-Schmidt process with v of 2 prime, okay, so we have with x of 3, so we have 2, negative 7, 0, 0, dot product with v of 2 prime at 1, 44, 10, and negative 3. Dot product comes out to negative 310. And again, taking the dot product between v of 2 prime and itself, taking the sum of the squares of 1, 44, 10, and negative 3, we have 2046. And so for the ratio of the dot products, now we have negative 310 over 2046 is equal to negative 5/33. So just taking what we have in the dot products. Okay, so again, we have x of 3, negative 2, negative 7, 0, 0, and we have minus 2 11ths, and again, times v of 1. V of 1, again, we have it minus 1, 0, 1, and 3. And then we have minus the next dot product ratio. Again, we had minus negative 5/33 times v of 2 prime. Again, v of 2 prime, we have 1, 44, 10, and negative 3. And combining what we have for the respective first, second, and third, as well as the fourth elements from each of the vectors that result. Okay, we have negative 5/3, negative 1/3, 4/3, and negative 1 to result. And to get rid of the fraction, we can extenuate v of 3 out to v of 3 prime. So we have the integers in this matrix at negative 5, negative 1, 4, and negative 3. All right, so we have our v of 1, v of 2 prime, v of 3 prime. And so we have with our orthogonal basis, okay, we have, again, so we have negative 1, 0, 1, 3. V of 2 prime, we have 1, 44, 10, negative 3. V of 3 prime, we have negative 5, negative 1, 4, and negative 3. And again, the dot products between the first and second, first and third, as well as the second and third vectors, these will result as 0. And again, for the orthonormal basis, okay, if I take each of the elements of the respective vectors and divide by, again, their respective magnitudes, okay, so dividing everything in the first vector, okay, by the square root of 11. Next vector, you have dividing by the square root of 2046. And the last, you have dividing everything out by the square root of 51. All right, now, so you have for a single matrix, and it says to find both an orthogonal and orthonormal basis okay, for the given matrix. And here we have a 3 by 2 matrix. First column we have at 2, 1, 0. Next we have 3, 4, 5. And if we use the Gram-Schmidt process, again, V of 1 is equal to X of 1. Now, X of 1 is going to be the first column, and X of 2 is going to be the second column. So we have our V of 1, that's equal to X of 1, which will consist of 2, 1, 0. Now, for V of 2, again, with the Gram-Schmidt process, so you have X of 2, which we have at 3, 4, 5. And for the dot products, okay, we have that between X of 2 and V of 1. Okay, we have 3, 4, 5, the transverse of it, times 2, 1, 0, and the dot product comes out to 10. And the dot product between V of 1 and itself, again, taking the sum of the squares, so 2, 1, and 0, this comes out to 5. And again, the ratio of the dot products we have at 10/5, which will be at 2. So we have 3, 4, 5 minus 2 times the vector, representing V of 1, which we have at 2, 1, 0. So we're going to have 3 minus 4, which is negative 1. And we have 4 minus 2 times 1, that will result as 2. And 5 minus 2 times 0 is 5 minus 0, which will be at 5. And so we have with our V of 1 and V of 2, we had the orthogonal basis, okay, where we have the vectors at 2, 1, 0 and negative 1, 2, 5. And again, taking the elements from each vector and dividing by the magnitude of the vector. So we have sum of the squares of 2 and 1 will amount to 5. Sum of the squares of negative 1, 2, and 5 will amount to 30. So we have translating from the orthogonal basis to the orthonormal basis. Okay, we come out to 2 over the square root of 5, 1 over the square root of 5, 0 for the first vector result. And for the second and last, we have negative 1 over the square root of 30, 2 over the square root of 30, as well as 5 over the square root of 30.